So you've got three example calculations then, and just measuring and calculating enthalpy changes. We'll have a look at the first one. Always a good idea with a calculation to identify the information you've been given to start with, and maybe even write that out. So you've already been given the number of moles of the compound. So we've got that value of N that we're going to need. So you haven't got to work that out. You're not even told what it is anyway. So N equals 0.05. The temperature change, well, it increases from 298 to 301. So I hope you can work out the temperature change. Whether it's positive or negative at the end, you don't have to come back to this. Of course, if you get an increase in temperature, what sort of change is it? It's going to be exothermic, isn't it? So the energy's been given out from the chemicals and it's gone into the water. So the actual answer will be negative. But don't do that until you get to the end, all right? Because it will confuse matters. So you've got your delta T is 3. Total mass of the solution is 220 grams, so you've got M. And you've also got a value for C. So if you did it in those 3 steps that we had yesterday, okay, for number 1 then, what we've been given is N equals 0.05. We'll need that eventually. We've been told that our delta T is 3 kelvins. We've been told our mass is, 220 grams. And we know that C is 4.18 joules per gram per Kelvin. That's right. Get into the habit of putting your units in. And so if we take our 3 steps like we had yesterday, I mean, you've barely got enough space to put all this on, as well as the steps. But the first step was to work out the temperature change. You're not going to have to work out the number of moles, of course, so step 2 is done. So first of all, Q equals MC delta T. So we've got the numbers for that. We've got the mass is 220. C is 4.18. Delta T is 3. Lining up your equal signs. Oh, I haven't lined them up with the top ones, but all right, so whatever that is. So I have a calculator that the battery has gone in. I'll do the job. Okay, 220 times 4.18 times 3. Hopefully we're getting 2758.8. Yeah, good. Okay. 2758.8 what? Joules. So we immediately need to turn that into kilojoules, which will be, certainly will, 2.7588 kilojoules. All right, no rounding yet. So that's the first bit that's done for us. N we've already got given to us. So we've got, so we know N is 0.05 moles. So we can quite simply work out our delta H. I'm not going to put the, well, I suppose we can have delta H naught. I'm not going to give it a subscript for this. We could just have reaction, but delta H naught will do. Oh no, let's be correct about decisions. So it's the heat exchange, the heat transference, divided by the number of moles. So we have 2.7588 kilojoules divided by 0.05 moles. So presumably that's going to be quite a big number, actually. So let's divide that by 0.05. Oh, it's not as big as I thought. 55? Yeah? Yeah, 55.176 units, kilojoules per mole. Okay. All right. So, you know, that as an example, hopefully then the others won't be any more difficult than that. So I'll let you have a go at the other ones on your own for a bit. Of course, because this is a rise in temperature, we also need to add a minus sign there. It's an exothermic reaction. The second example I'll work through, and then we'll have a bit of a closer look at the third one. You are given, well, we haven't really got space to write all the details out, but if you do step 1, that's the Q equals mc delta T. You're given the mass. This is the substance that's warming up. The heat's being transferred into the water, so you've got 200. The C doesn't change, 4.18. So I could put all the units throughout this, but that would be going a bit too far. 29 kelvins rise. So I made that 24,244 joules. Yeah. So that's 24.244 kilojoules. We then had to work out the moles of whatever it was we'd got, pentane. And we're told that we've got 0.5 grams, but we're told that its formula mass is 72. So that saves us having to work it out, which gives us a not very round number, does it? Really, it's I got 0.0069444. I suspect it's supposed to be rounder than that, but we don't round yet. And then we can do our calculation. So step 3, delta H, this time, delta H naught, we're told it's combustion. All right, so we can put the little C down there. So we've got Q divided by N, which is our kilojoules. So that's our 24.244. Whoops, lost the point. Divided by, I still lost it, it's in there, all right. Divided by the number of moles, so that number, which say may have been rounded at some point. And what I came out with was 3491.1583. You might not agree exactly, it depends where your calculator has stopped working it out. Yeah, okay. Yeah, depending on where it stops in terms of decimal places, then you know you'll get slight differences here. Of course, again, because this is a rise in temperature, the chemicals are losing heat into the environment, so it's another negative one. And units, of course, kilojoules per mole. All right. So hopefully, if you've gone astray in any of that, then you can you can check it off. The third one, all right, I'm going to give you a bit longer to have a look at that one because it requires you to work backwards a bit. You can work out the energy change, all right, because you've got the M is 300, C stays the same. You're told that the delta T is 55. So you can work out Q, MC delta T, you've got that. But they've given you a value for the enthalpy change. So you've got to remember that enthalpy change is Q, which we've worked out, divided by the number of moles. We've got 2 of those things, so we can work out the number of moles, and from the number of moles you can work out the mass. All right, so it takes possibly a bit more space than you've actually got down there, but I've managed to fit it in, so I'll give you a little bit longer to play with that one and see if you agree with what I've got. Okay, let's have a look at that third one then. The information that you're given in the third one, all right, you're unusually told that the delta H value is minus 5,512. We don't need the minus when we're doing the calculations, but that's just the information we're given. We're told M equals 300 grams. We're told we know what C is, that's constant, joules per gram per Kelvin. Whoops, that was a very small K. And we're told our delta T is 55. So we can immediately work out Q equals, right, if we were going to do it properly, MC delta T, multiply that lot together, you get, I'm not putting the bit in between, 68970. Okay, so that's our joules. So that's 68.97 kilojoules. The next step is to think, well, what else do we need then? We're given the delta H, right? I'm not going to put the bits in, but delta H is Q divided by N. Well, actually, we've been given the delta H. Here is where we don't need the minus sign because it would give us a negative amount of a substance or a negative number of moles, so it's pointless. It is just an energy change, and when we don't need to express, it would be the same if it was an endothermic or exothermic reaction, wouldn't it, in the calculation. So we've been told that 5512 is 68.97 over N. Now, to rearrange that, it's interesting, isn't it? That's a real simple rearrangement. And if you're going to look at it algebraically, you multiply both sides by n, then you divide both sides by 5512. But it's interesting how people just look at that and just go completely blank. If you get that blank feeling when you're rearranging something like that, just put some simple numbers in. So my sort of maths hint over here would be that we know, for example, that 3 equals 6 over 2, and you can rearrange that perfectly well, can't you? You know, so you know that 2 equals 6 over 3, and 6 equals 2 times 3, and so you just, you know, take the positions and use the same approach. So here, if we're saying 3 equals 6 over 2, and we want to get that number, well, n is, you know, that the 68.97 divided by 5512, and you know, you can work it out, or you know, you just remember these things. How to rearrange. But yeah, it's like the triangle sort of approach, isn't it? So that gives you the number of moles, which is not a particularly round number, is it? Again, all right. So that's the bit that we can work out from that, which I have here somewhere with 0.0125126. 125126 is what I got. All right, so that's how many moles. Now, we've also been told the formula mass of the octane, as it is. It can, change propane to octane. So the mass, it's going to be, well, it's that many moles. 6 multiplied by the mass of a mole, which is 114 grams. And so we come out at somewhere around 1.426 in some bits, so I'm going to round that up. All right. So, yeah, this is why you have to do maths on a course like this, isn't it? You see, this unit has got a lot of calculations in it, so that's not an unusual type of thing. All right. So, it's easy when you you just look at it like that, isn't it? Right. The next thing then is about allowing for heat loss. Obviously, if you're using a calorimeter, the idea is to try and keep the temperature change of your water inside that, if you're trying to measure a maximum temperature change. If you are calculating the energy content of some food, for example, they use these big insulated calorimeters that do that. But very often, if it's a glass beaker or something like that, then you're going to have heat losses to the environment. You're going to have heat losses to the container, heat losses to the air. So we have to find a way for allowing for this. And It's not something we can do with the one that you're looking at this afternoon. The idea of the thermometric titration is actually to show you a type of practical measurement that is a little bit harder to handle, and then next week you'll do one where you can use the technique that I'm about to show you. So this idea of allowing for heat loss. Most obvious with an exothermic reaction that's sort of giving heat out to the atmosphere. But also, of course, with an endothermic reaction, if it's taking heat out of the water, well, you've then got a temperature gradient between the water and the air, or the water and the container. So equally, it could be taking heat energy from the container or from the air. So it's heat loss is it's half the story really, but it is the same. Now, if you took, for example, a reaction between hydrochloric acid and sodium hydroxide, which is the one you're going to do this afternoon, but you won't be able to do this because you're going to use a well-insulated, you're going to use a polystyrene cup, basically. But if, for example, you did hydrochloric acid and sodium hydroxide, all right, that's that's a title rather than an equation. The way you would do it, if you were using a little beaker and you did this just adding it using the little measuring cylinders in the last unit, just to get the idea of endothermic and exothermic reactions. What you did, just as a reminder, you measured the temperature of the hydrochloric acid it could be every 30 seconds or every minute for 2 or 3 minutes to start with, to make sure it was at a stable temperature. So if we started with, let's say, the hydrochloric acid, and let's say we measure it every 30 seconds for, let's say, 3 minutes. It's not set in stone, this. Okay, that's just to make sure that you're starting at a stable temperature, because it might be that the hydrochloric acid has been taken out of the chemical store. The chemical store doesn't have a heater in it, so it could be cooler than the lab temperature. So it would be on its way up to lab temperature. As it happens, what we're using today has been standing around in the prep room and in here, so it will be at the right temperature. It should be fairly stable. But just to make allowances for possible warming up. You then add your sodium hydroxide, and this is if you are adding it all in one go. All right, now that's not how your titration is going to work this afternoon, because with a titration, you run a bit in, you run a bit more in, you run a bit more in, all right, from the burette. All right, so that's not going to work for this. But this is if you add it all at once. Okay, so this is all at once situations, because the rest of the practicals that you're going to do will be where you add it all at once. All right, this afternoon's is just to show you another option. And once you've added that, you can't measure the temperature of the reaction that takes place exactly at that point. So on your time scale, you actually end up with a gap, really. And you then keep measuring the temperature. And again, it could be every minute, it could be every 30 seconds. But I have put this as an example, so it's not the only way to do it. So it could be every minute for, I don't know, let's say 6 minutes. It's usually enough, actually, although we do find with the one that you do in the assignment, for some reason it can go on for ages. The temperature change is very slow on it. What will happen is that the temperature will rise quite rapidly, and you might remember seeing that in those little beakers when you added one substance to another. You got quite a quick temperature change, and then it sort of slowed off, and then it started cooling down again. So what you get is temperature rises rapidly, for this particular reaction, it rises, all right, it's an exothermic one, gives out heat. So it rises rapidly at the start, as the reaction gives out heat. Then it drops slowly and regularly as the heat is lost. Now this means we actually want heat to be lost, but we can use the heat lost as a way of allowing for it. So then drops slowly and regularly as heat is lost. Now that means that with this sort of reaction, you don't want too much insulation. You don't actually want just to keep the heat in your reaction mixture. You want the heat to actually be lost so that you can make an estimate. I'll show you what I mean. What you have to do is to graph the temperature change. We have, if this is our, whoops, oh, I should really use the straight line tool on here, shouldn't I? If this is our temperature, doesn't matter whether that's degrees C or kelvins, they are essentially the same. And that's time. All right, so temperature and time. What we've got from our results is, well, we've measured the temperature of the hydrochloric acid every 30 seconds for 3 minutes. So, well, let's take our first measurement as time naught. So 0, 30 seconds, 1:30, 2 minutes, 2 minutes 30, 3 minutes. At that point, we add our sodium hydroxide, or at the next 30 seconds, we add it, actually. So here is going to be where we actually add the sodium hydroxide. Now, you can't get, it's not an instant reaction, right, that instantly raises the temperature of the water, but you will get an increase in temperature. Now, it might happen immediately, or it might take a couple of readings before it all the heat gets into, whoops, they're a bit close together, the reaction mixture, but you will probably get this sort of effect. Now, I have a bit of a problem here because I've drawn this too high up, too close to the words. Never mind, you'll get the general idea. How can we work out the actual maximum heat produced by that reaction at this point? This is the point we want to know at this point, which is, this is our actual mixing. That's the point where we mix the two together. That's where we want to know. That was the maximum heat, but we didn't manage to get it because it took a while to transfer into the water and then it was being lost. Well, the way it works is if we draw a vertical line up here, all right, this is the point that we're going to want. Sorry, it's going to go up to the words there. We extrapolate. Extrapolate means you extend the line, and it's this line that we're going to extend. So it's going to go like that. All right, you draw it back through the starting point, and then you can read off, if I just extend that up there, the change in temperature will be, if that's your starting temperature, that is theoretically where the temperature would have got to if we'd been able to measure it at that point. So this is now delta T. So you've actually got now a way of allowing for the heat loss. So what you're doing here, you're extrapolating the line to the point, the time at which you mixed, because you can't physically measure all the heat that's given out because it doesn't, you know, it's just not there at that point. Then, yeah, you get a good estimate. I mean, that's all it can ever be, is an estimate, isn't it, really? All right, so this, yeah, this is called extrapolating. All right, that up there. So extrapolation. There are some circumstances in which you know, you are justified in extrapolating like that, and then other cases where you're not. You know, you have to think, for example, when you're drawing graphs sometimes, is it realistic to draw it back to the origin, you know, 0, 0, because it's not always, is it? And usually if you're doing experimental data, then you wouldn't extrapolate, you just keep within the points that you've measured, because you've got no way of, you know, supporting you know, any line outside that. But for this one, you actually have to use the extrapolation to estimate what's going on. If you were looking at a cooling, you know, where you've got an endothermic reaction, I've got to try and get this one right. We would have, all right, these might not be at quite the right intervals, but you would have, if that was your starting point, you'd have, and then we've got mixing about here, say, you might have cooling that continues for a couple of readings and then starts to come back to room temperature. So you get that sort of effect. So if this is our mixing point for an endothermic reaction, this time, of course, we're going to extrapolate back this bit. So we would estimate our temperature drop as being here to here. Sorry, I should have put that across. So this time that would be your delta T. All right, you've got a negative change there. And it would be nice if the points were that steep when you do them, to be honest, but you tend to get very flat lines. Now, one of the biggest issues that you have with this, I'll flag it up now, is how the heck do you draw that using Excel? All right, now we haven't necessarily totally cracked this because we don't want one line on there, and you can't easily get Excel to draw a line through some of the points but not others. There are various ways. You can, of course, use a drawing tool to actually, you know, put your own lines onto a graph. If you just plot the points, you can just plot the points, print it off, and then draw them on by hand. If you do that, well, either of those actually, you are putting on your own line of best fit through this extrapolated bit, aren't you, really? And that's quite tricky to do. And what I've suggested to people in previous years is that to work out the line of best fit just through, let's say, these 6 points up here, so that you can extrapolate, is plot those on Excel on their own and get it to do a trend line, and then visually, you know, transfer that, you know, with a drawing tool onto the actual graph. It would be wonderful if they actually came out in a nice slope like that. In fact, they don't. You get flat bits. You'll find, you know, I'll have people constantly saying, oh, mine stayed the same temperature for 2 or 3 minutes, and then it's dropped a little bit, then it stayed the same again, then it's dropped a bit more, and this is what happens in real practicals. You know, they don't come out like that. The one that you're going to do next week, which is mixing zinc powder with copper sulfate solution, you will get a reasonable graph for that, and you'll be able to do the calculation. You'll be able to get an enthalpy change for that. But yeah, the ones for the assignment, a little bit trickier. So that allows for heat losses, or whatever the reverse of heat loss is, heat gain from the environment, I suppose, in this situation. By making an estimate, but the next thing we're going on to doesn't really fit in with this, so we'll leave that aside now until next time. Just as a reminder, because what we're going to attempt then is a thermometric titration. Titrations, recap on titration, typically used for acid plus base or acid plus alkali reactions. It's not the only option. We use them for other reactions as well. So typically what we're looking at is neutralization. And a neutralization reaction, well, the one that you're going to do, we just use this one over and over again. So you've got your hydrochloric acid, aqueous, I think we had this yesterday. Sodium hydroxide, also aqueous. Giving us our sodium chloride, I remember, yeah, that was aqueous. And of course our liquid water. All right, that's an L at the end there. Unless I've invented a new state. What we're looking at, the idea of neutralization is the hydrogen here, the hydrogen ion there, and the hydroxyl ion there. All right, this is our actual neutralization. The rest of it is just, watching, really. That's the actual reaction that we're looking at. We reach a point, I think it's learning outcome 2, where we're doing the rates of reaction, where we do start needing to miss out some of the components of reactions like this. And those bits that are not included there would be described as spectator ions, all right, because they're not actually the important part of the reaction. The important thing here is we have an acid. The acid is hydrochloric acid. Hydrogen ions define the acid. The base, the alkali in this case, because it's soluble, the hydroxyl ions are, the bit that are going to react with the hydrogen ions. The chloride ions and the sodium ions, well, they don't change. Over that side, they are still, I suppose that's the best way to actually put it in. All right, if I put them in here, they are still, when they get to this side, in solution, they are still that. All right. All right, so the green bits are not important. The sodium ions are sodium ions on both sides. They haven't changed. The chloride ions are chloride ions on both sides. They haven't changed. The hydrogen ions, however, are not hydrogen ions on the other side. The hydroxyl ions are not ions on the other side. All right, they have formed covalent bonds in the water molecule rather than being ions. So that's the reaction. Okay, now that's sort of jumping ahead to several other things that we're going to do in this unit, but sometimes it's important just to extract out the little bits that are really representing the reaction that's taking place. So neutralization is the point at which hydrogen ions and hydroxyl ions equal each other so that we can put them together and make water molecules, and there's no excess of one or the other, making the solution acidic or alkaline. And we do it using the burette. And a reminder, all the usual sort of technique bits with the burette. So you've got your burette with its tap in its stand. Okay. We have, I think, get it the right way around. The acid usually goes into the burette. And the acid we are going to know the concentration of. All right, so the acid's going in here. We are given hydrochloric acid at a concentration of 2 moles per decimeter cubed. You're going to run hydrochloric acid into sodium hydroxide. Now, before, you used a conical flask and you put an indicator in it. This time, you're not doing that. Right? You're going to use a calorimeter. Ugh. And the calorimeter is polystyrene cup in a beaker. All right? So this is our, I suppose I could have put the beaker around that as well. Let's have the beaker standing there. All right. So this is, it's going to be a known quantity of sodium hydroxide. Our original instructions said 15, but we're going to say 30 centimetre cubed. All right. Now, that you need to just be as accurate as you can. We don't have pipettes that will measure 30. So it's going to have to be done, we could get you doing it sort of, 3 lots of 10 or whatever, but it's not going to be that accurate anyway. So you can use a measuring cylinder. 30 centimetre cubed of sodium hydroxide, okay, in there. And that's what we're trying to work out the concentration of. So we're going to run hydrochloric acid into this until we reach the neutral point. How are we going to identify the neutral point then if we haven't got an indicator? It's the volume of hydrochloric acid that's added that brings us to the maximum temperature. All right, which means you're going to need a thermometer in here. So the thermometer is going to sit in there. And you're going to need to be careful about running the hydrochloric acid in, because you will reach a point where you've hit the maximum temperature and then you add a bit more and it'll just sort of stay at that maximum temperature. You've got to, so it's when it plateaus out really, and it'll need to go on a graph. We haven't drawn a graph for a while in this, have we? So 30 centimetre cubed of sodium hydroxide in the cup. Measure its temperature. All right, the temperature of what's in the cup is important. You're just going to add the hydrochloric acid, perhaps no more than 5 centimetre cubed at a time. It might be less than that, perhaps 2 or 3 centimetre cubed. But you can sort of add the first bit relatively quickly, I suppose. You could do perhaps, I don't know, 3 lots of 5 and then cut it down a bit. Once you've added it, record the temperature, or give it a little swirl, record the temperature, add a bit more. You've got to do it quickly, all right, because, of course, you're going to keep losing heat to the air. What we can't do with this, unfortunately, is put a lid on it. We do have lids. We have little wooden lids that you can put a thermometer through, but, of course, you can't run the acid in from the burette through them as well. So we can't, we can't keep the heat in very easily. It's that's one of the issues with this. It's a theoretical technique, but actually in reality it doesn't work brilliantly. So it's a good example of what are the problems. So it's a matter of running in the hydrochloric acid. Say 5 centimetre cube, measure the swirl, measure the temperature. Another 5, swirl, measure the temperature. Do it fairly quickly, and then cut down the amount that you're adding in each time. But keep recording the temperature each time you've added some. What we're not doing here is recording anything to do with time. All right, we are recording amount of hydrochloric added on the x-axis, aren't we? And then the temperature on the y-axis. And hopefully we should get, well, I'm not sure quite what we'll get. You never can tell from one year to the next, to be honest. So 30 centimetre cubed of sodium hydroxide, that's easy enough. Use a burette to add small amounts of hydrochloric acid. Swirl the solution, measure the highest temperature, add a second amount, swirl, measure the highest temperature. Continue until there are enough readings to decide the highest temperature for the experiment. Okay, so you can draw a graph of your results. Once you've got we could work out the enthalpy change. Well, you'll have, your total mass will be the acid plus the alkali. We'll have a temperature change. You should be able to do it. We'll see. It's worth a try anyway. You need eye protection for it because the hydrochloric's a bit more concentrated than we normally use. And sodium hydroxide is always nasty at pretty much any concentration, to be honest. At corrosive, I would, I'd be wearing a lab coat as well. All right, so lab coat and eye protection, and give it a go. Now, in terms of working, James and Sonia, do you want to work together? You won't fight, will you? All right.